Okay, let's do another example that involves springs and blocks sliding around. Okay, so you have two blocks, and let's say, oh, the cuts are for YouTube. Basically, they'll just be different videos. So instead of having an hour and 20-minute video, there's like, 4 20-minute videos, or however long it ends up being. So two blocks of the same mass are sliding towards each other on a frictionless surface with the same speed. Okay. One of the blocks has a spring attached that provides, so when they collide, and they will collide because they're going towards each other, all the force between the two is going to come from the spring. Right? They're not going to like so compress the spring that they start touching each other. And so then the question is, after the collision, what are the velocities of the blocks 1 and 2? So again, let's do the same thing. Let's think about, this time there's only one before and after, right? There's before they collide, and then there's after they collide. So while they're colliding, from before to after, what's going to be conserved? Okay, if the slides disappeared, I can just try to reshare them. Sometimes this happens. Again, I'll go back to the setup for a second, if people are thinking, and then put up the ABCD. Yeah, so I put this question back up on the slides, but it's why, what is conserved, right? There's going to be a collision. So before they're touching to after they're moving away from each other, okay? Those are before, that's our before and after for this two blocks with the spring collision. And so what is conserved during that collision? Okay, why don't we just think about it for a little bit more, maybe 30 seconds. Okay, let's go. wrap this up with 3, 2, 1. All right, so most popular is A with a C close behind. So almost everybody thinks that energy is conserved, right? And that's good, right? Energy is conserved here, right? Because if you think about the forces, right? So they're going to collide, right? The normal force and gravity are acting vertically, and nothing's moving that way. So they're not going to be able to do any work. There's no friction, right? All the force that acts is from the spring, right? And the spring is a conservative force, right? It has a potential energy. So it can convert, while during the collision, the kinetic energy can convert into spring potential energy, but then the spring can give that all back, right? So it's right that energy is conserved, right? But then about momentum, right? So the difference between A and C is that C is saying momentum is not conserved, right? Well, it's the same thing. If you think about the external forces, right? There's no external force outside of the two blocks, right, in the horizontal direction, right? There's just the normal force and gravity in the vertical direction, which we're not worried about, right? So you are going to conserve momentum as well in the collision, right? So A was the right answer. So it's good. That was the most popular, right? And really that's the difference, right? So for energy, we had to think about the spring because it was an internal force, but it could potentially change the energy, except for the fact that it's conservative, right? But for the momentum, we just have to think about the external force, right? And that the external forces are not going to be changing the momentum of the system. If I actually were doing this in real life, I realize this slide is for actually trying it. What's going to happen? We're a little low on time. I did want to talk about the pre-lectures if we want. But is there any other questions about the conservation for the colliding blocks? Okay, so again, we don't have a lot of time left. Yeah, why is momentum conserved? Again, right? So when they come to collide with each other, right, to not conserve momentum, you need an external force that acts on the system for some time, right, in the direction that you care about. So I care about the horizontal direction here when they go in and they collide, right? And there's just no external force in this case, right? If it's frictionless, there's no friction acting. Gravity and the normal force are vertical, right? And so they're not going to change the momentum in the horizontal direction, right? The spring is internal to the system, right? And so the combined momentum of the two blocks has to be conserved. Right, again, this is another good problem to actually sit down and do the math, but we're just running short and I wanted to say a couple more things. You'll do a very similar problem to this as well at the recitation. Again, and that's the big thing. So momentum in some sense is simpler because you just have to think of, are there external forces acting on the system in the direction you care about? And even if there are, though, if it's like a really fast explosion, we'll just say momentum is conserved because there's no time for them to change the momentum. Energy is, again, a little more complicated, right? You have to think about, are the forces conservative? Are there external forces acting on the system and doing work? But also, you have to think about the forces between the objects, right? So things like friction between them or things sticking together basically will say right away that objects are not, that energy is not conserved, right? And so that was on the pre-lecture. Yes, if they're equal mass and they move with equal and opposite velocities and collide, you can lose all the kinetic energy. So most people were right. And that's what happens when they stick together. We did actually see this before spring break, I think, with the cars, right? That they stuck together and stopped, right? And that conserves momentum because you go from zero momentum where they canceled out, each having some momentum, to having zero because nothing's moving. And that loses all the energy. So you can do problems like that. There's also one important word that's used on the recitation. So you can also have energy conservation when we tell you that you have energy conservation. So we'll sometimes say that there's an elastic collision. And this really means that the forces involved are going to conserve energy. But it's extra information that we have to tell you. So if you see that word, that basically is a giveaway that energy is going to be conserved in the collision. Right? And that was what the pre-lecture question 2 was about. So if you have a moving object collide with a stationary object with the same mass, right, and the moving object comes to a stop, this is going to conserve momentum. So the one that wasn't moving is going to start moving with the same velocity. And that means that the kinetic energy is the same. And so you get an elastic collision. And that was good, actually, that 70% of the people answered got that, because that one is a bit tricky because it involves a few different concepts working together. Yeah. Okay. So since we're almost out of time, I just want to stop there. And if there's any other questions to answer that you'd like answered about this stuff, go ahead. Okay, so I guess if there's nothing else, no other questions, yeah, I guess thanks for coming, and we will see you next time.